Okay, so just to recap, I just summarized again those 4 thought experiments and the equivalence principle, and now we'll study them mathematically. So from a mathematical perspective, okay, this is Newton's laws in a gravitational field. Mx double dot is equal to minus mg. So I'm assuming the upward direction is the positive x direction and g is the magnitude of the gravitational field. Okay, so this is the positive x direction, g is this way. The vector g is this way, and this describes Newton's laws, which is mass times acceleration is the force seen by an inertial observer in a gravitational field. This is due to the gravitational field. And the key point is that the inertial mass, that is the mass that appears on the left-hand side of this equation, which has to do with the resistance to any force, not just the force of gravity, that appears over here. And on the right-hand side, you have a force of gravity, and only in the force of gravity, the mass that appears here, if you call it gravitational, it's like the gravitational charge. This is exactly the same as the inertial charge. Okay, it's exactly the same as the inertial charge, or the inertial mass. So the fact that these two are the same is the key insight. Okay, and what that means is every object, no matter what its mass, will experience the same acceleration. Okay, every object will experience the same acceleration due to gravity in a uniform, whether it's a bowling ball or a feather. In the absence of air resistance, they all follow the same rate. Okay. So now what you can do is, instead of working in this inertial coordinate system of x, you can switch to an accelerated coordinate system. That is, you can switch to a coordinate system y. So positive y is still in this direction, but y is such that if this was y is equal to 0 and this is x is equal to 0 at the initial instant of time, okay, the coordinate y is such that it's also, you can think of this as a freely falling reference frame. Okay, so that is the y is equal to 0 point. Okay, moves to sorry. Sorry. Okay, so let's imagine a reference frame which is accelerated downwards. Okay, so it's freely falling, so it's accelerated with this acceleration g. Okay, and now we want to know how to describe the coordinates y of some particle in that freely falling reference frame. So this is not an inertial reference frame. Okay, so in this non-inertial reference frame, okay, this is the coordinate transform that you use to relate the y coordinate in the accelerated reference frame or the freely falling reference frame to the x coordinate of the inertial frame. Okay, so this is in the accelerated frame. This is of the inertial frame. Okay, and when I say accelerated, it's freely falling reference frame. Okay, so it's falling in this gravitational field. Okay, so imagine a coordinate system that's falling in this gravitational field. So, so now basically, yeah. So what happens is, if you're puzzled by the sign, so as your coordinate system drops, okay, so your y is equal to 0 is at a lower point. So if I want to describe the same x coordinate appears to be moving upwards, and the amount it moves in a time t is this extra distance, half gt square. So the y coordinate would be described as whatever my x coordinate is, which is this, plus this amount that the coordinate system has dropped. Okay, which is how the origin of the coordinates is dropped by an amount of gt square. Okay, so that would describe my net y coordinate. Okay, so now I can take this equation, differentiate twice with respect to time, and what that tells me is y double dot is equal to x double dot plus g. Okay, and this is now from the Newton's laws of dynamics, okay, if there were no other forces acting on particles, then x double dot is equal to minus g. Okay, that's something that we know, and therefore if we apply Newton's laws in the inertial reference frames to this equation, that tells us y double dot is equal to 0. Okay, so in other words, in the freely falling coordinate system, okay, my double dot is equal to 0. So what this means is this is exactly what you'd expect for Newton's laws in an inertial reference frames with no forces acting on you. With no forces. Okay, so the point is that free fall, okay, free fall in a uniform gravitational field gives you the same dynamics, okay, same dynamics for Newton's laws as you would experience in an inertial reference frame. Okay, that's just a mathematical way of saying that picture 1 here and this thought experiment 4 here are exactly the same. Okay. Mathematically, the key thing that we had to do was make this kind of transformation of coordinates. Okay. We had to take y is equal to x plus half gt square. Okay. This is transformation to an accelerated frame of reference, but as we've seen before, even if you go to curved coordinates, okay, which as long as if your transformation is non-linear, okay, you will get pseudo forces. Okay. And even in terms of x and t, if you think about this transformation, of course, this is in these are sort of Galilean. We're talking about Newtonian mechanics, okay, not special relativity. But even then, if you're making a nonlinear transformation of y and relating it to x and t square, okay, this is going to give you some kind of extra pseudo forces, and these pseudo forces cancel out the effect of the gravitational field. Okay. Okay, so this is as far as a uniform gravitational field goes. Now the question is, what happens in a non-uniform gravitational field? Okay, is there any way to tell that you're in a non-uniform gravitational field? And the answer is yes. Okay, so suppose, again, let's consider this thought experiment of falling not so close to the surface of the Earth that you can approximate the gravity as just downwards. Really, what we know is if you're sufficiently high, then you will see that the force on this apple, let's say, acts towards the center of the Earth. The force on this apple acts towards the center of the Earth, and the force on you acts towards the center of the Earth. Okay, and these directions are all slightly different. They're not all straight down. Okay, they're all slightly different. They're these are slightly tilting inwards. Okay, so this is what happens in a non-uniform gravitational field. Okay, so now you have forces which are not all in the same direction. Okay, they can act in different directions, and moreover, you can have other things, right? Like the magnitude of this force doesn't have to be the same as the magnitude of this force, right? They can be slightly different magnitudes and slightly different directions. Okay, now what does this mean for the person in the elevator? So let's imagine that the elevator is once again in free fall. Okay, and if you're falling down, what would happen? Okay, now what it means is in the elevator, which is in free fall, of course, if everything was in the downward direction, it would be like you're an inertial observer. Okay, you're just standing here. The pseudo forces act oppositely to the direction of the free fall, and therefore in the elevator you don't feel like you're an inertial observer. However, because the forces are not all in the same direction, okay, either not in the same direction or not of same magnitude, what would happen is these apples in the frame of the elevator would appear to slowly come closer together. Okay, they would slowly come towards you. Okay, as you fall, because as you fall, now the elevator is the same size. Okay, but the apples have sort of moved closer together to you. Okay, so in the elevator, it looks like you had two apples sitting here. Okay, and these apples are moving towards you. Okay, so this is a bit strange. Okay, so imagine that instead of being an inertial observer, now what you find is that apples which are this way seem to be attracted towards each other. Okay, they seem to be attracted towards each other. Okay, now this kind of effect is called a tidal force. Okay, so I'll explain what I mean by tidal forces, but this kind of effect is called a tidal force. Okay, and this is an effect of gravity. Okay, which is real in the sense that you cannot eliminate this force by going to a coordinate system which is non-linear or accelerated. Okay, this force will somehow show up in some way. These tidal forces are real, they're physical manifestations, right, of what you will see. Okay, so these tidal forces are like the physical manifestation of a non-uniform gravitational field. Okay, so there is a physical effect of gravity. Okay, it's not just due to a change of coordinate system. Okay, but to see this effect, you can't just look at one apple. You have to look at different objects in free fall and see what the tidal forces on them. Like, do they come towards each other? Do they move away from each other? I mean, of course, if you're freely falling with the apples, right, you are almost like an inertial observer because this is only almost like a uniform gravitational field. It's only because of the non-uniformity of the gravitational field that you'll see the apples coming together. That's how you detect the presence of a non-uniform gravitational field. Okay, and that is physical. That's not just an artifact of your coordinate system. Okay, so that is the physical effect of gravity. Okay, so now let's come to the statement of the equivalence principle. Okay, this is one way of stating the equivalence principle. There are multiple ways of stating it, but this one will do. Okay, for us. So the equivalence principle is this. So at every space-time point in an arbitrary gravitational field. Now we're not making the requirement that the gravitational field is uniform. Okay, it is possible to choose locally, okay, that is in some small enough region of space-time, to choose a locally inertial. And what do we mean by inertial? Freely falling in the gravitational field coordinate system, such that if you're in a sufficiently small space-time neighborhood of the point that you started with, the laws of nature, okay, will take the same form as in the unaccelerated, okay, that is the one which is experiencing gravitational field, unaccelerated Cartesian, by Cartesian I mean orthogonal coordinate system, in the absence of gravity. Okay, so this is basically the, for example, the second part is laws of nature which take the same form as that of an unaccelerated Cartesian coordinate system in the absence of gravity. If we take the laws of nature to mean Newton's second law, okay, then we're saying that the forces that you experience on every object that you test on, you would find Newton's second law to hold. Okay, and so the second part of the statement is laws of nature being, for example, one example is F is equal to ma, and they take the same form as in the unaccelerated Cartesian system. This is the form in the unaccelerated Cartesian coordinate system in the absence of gravity. So there's no gravitational forces included here. Okay, every force except gravity is included on the left-hand side. And the claim is that even when I have a force of gravity, okay, what I can do is I can always switch over to a freely falling coordinate system. I can change my coordinate system from, let's say, x to y, such that I can get rid of this force of gravity, okay, and in a sufficiently small region of space-time, okay, it's possible to do this, so that the laws by a coordinate transformation, a nonlinear or accelerated, switching to a nonlinear accelerated coordinate system, where these forces are due to everything except gravity. Okay, so it'll look like I'm just recovering laws in inertial frames of reference. Okay, so that's the statement of equivalence between a gravitational field. If you switch to the appropriate coordinate system, which is freely falling in the uniform gravitational field, the laws will take exactly the same form as that of an inertial observer. So in other words, if you just change your coordinate system, there's no way of telling the difference between freely falling in a gravitational field and being an inertial observer. Okay, so that is the statement of the equivalence principle. Okay. Now, there are slightly different versions of the equivalence principle based on the assumption of what you mean by the laws of nature. Okay, this example that I gave you of the elevator, the laws of nature meant a very specific thing. It meant Newton's second law, F is equal to ma. And specifically, the example that we did actually only showed this for really Newton's second law in the form of Galilean relativity, not in the context of special relativity. Okay. So the different versions of the equivalence principle are assumed to, first of all, hold in the framework of special relativity, not just in Galilean relativity. And the weak equivalence principle is assumed that this statement of the equivalence between freely falling in a uniform gravitational field and inertial observers, the weak equivalence principle says that equivalence is true for Newton's laws. Okay, that's by just the observation that inertial mass is equal to gravitational mass. So this is a weak version of the statement. A slightly stronger version of the statement is that this applies not just to Newton's laws, but also laws that govern, for example, things like electrodynamics. So it applies to Newton's laws and Maxwell's equations as well. Both these laws, there's no way to do any experiment where you can tell the difference between light falling in a gravitational field, light in a gravitational field, in a uniform gravitational field versus light as the laws that light obeys in an inertial reference frame. Okay, and an even stronger version of the equivalence principle is not only does this apply for Newton's laws or Maxwell's equations, but it even applies to the laws of gravity themselves. So what do we mean by that? Imagine an object like the Earth, okay, which is bound together by, let's say, its self-gravity. And so part of its mass or its energy comes from just the mass of particles, but there's also gravitational binding energy, okay, which reduces the energy. Okay, and the claim is that if the Earth itself were freely falling in a gravitational field, okay, the laws that determine that gravitational binding energy, that itself, okay, would be subject to the equivalence principle, which is the laws of gravity themselves are subject to the equivalence principle. Okay, that is, there's no way to tell, okay, whether the laws of gravity are being described in an inertial frame of reference, a freely falling frame of reference, or in uh, or in an inertial reference frame. Okay, there's no distinction between the two. Okay, so for the purposes of general relativity, okay, Einstein basically took the assumption of the strong equivalence principle, where these laws apply not just to Newton's laws and Maxwell's equations, but he just assumed that the equivalence principle applies to every law of nature. Okay, so, and at the time, the things that were known were Newton's laws, Maxwell's equations, and whatever was to be determined about what the right gravitational laws are. Okay, so for the purposes of what we're going to do, we'll just assume that the strong equivalence principle, basically, in this equivalence principle, laws of nature are all laws of nature. Okay, they take the same form in a freely falling. For a freely falling observer in a uniform gravitational field as for an inertial observer. Okay, so general relativity assumes the strong equivalence principle. Okay, I'll pause for questions here.
Hello, sir.
Yeah, go ahead.
Yeah, sir, in non-inertial frames, we get pseudo forces, and in freely falling object, because of pseudo forces balancing the gravitational force, we get the frame as an inertial frame. So kind of we are going in circle over here. So,
No, but see, there's something very special about gravity, right? This would not be true, for example, if you had electromagnetic forces. Okay, because if you have let's say an electric field. Okay, now positive charges in an electric field would flow along the direction of the electric field. Negative charges would flow opposite the direction of the electric field, and they would flow in proportion to the strength of their charge. Okay, this is Q, this is Q prime. Okay, and now what this would mean is if I apply an acceleration. Okay, the question is I could always switch. So I could imagine that I switch to an accelerated frame of reference. Let's say the acceleration is this way. Okay, or I can take the acceleration to be downwards. Okay, in which case I would get pseudo forces, but the pseudo forces would act on both these objects in the same way. Okay. So what would happen is the pseudo forces in this case would not cancel the electromagnetic forces. Okay, so what you would see is that there's electromagnetic force and there's this also the pseudo force. Maybe if you chose the right magnitude of this acceleration, or you switch to an accelerating reference frame where it cancels on this charge, it would not cancel on other charges. So there are experiments that you can do which could test that you are in an accelerated frame of reference. Okay, but the point is, for gravitational forces there is no distinction.
oh, okay, sir.
Okay, more questions?
Hello.
Yeah, go ahead, Utkarsh.
So in our strong equivalence principle, we are trying to find a universal law of gravity which describes the effect of it, not the law itself about gravity. Like you said, gravitational binding energy. So
yeah, so okay, so to be clear, see, the strong equivalence principle you should think of as morally on the same footing as the principles that Einstein assumed for special relativity. Okay, so just like Einstein assumed inertial observers plus speed of light is constant. Okay, these are principles he assumed from which he derived, the laws of gravitation. Okay, sorry, the laws of special relativity, or the dictionary of special relativity. And it was a statement which the laws of nature need to obey. It doesn't tell you what the laws of nature are, but it tells you, for example, how that you have to modify Newton's laws, or Maxwell's equations have to be consistent with this dictionary of special relativity. Okay. Now, similarly, the strong equivalence principle is not a law of nature. Okay. Rather, you should think of it as a principle which will be used to derive a rule which laws of nature have to obey. Okay, and the question is which laws of nature, and the strong equivalence principle basically says all of them.
okay.
Malvika, I saw your hand up. I don't know if you still have a question.
Yeah, I had my hand up because I sort of didn't like catch this part properly, so that's why I have this confusion. But why are we treating gravitational laws like differently here, as in?
Uh, where? In the strong equivalence principle or earlier
Yeah.
when we just talked about the equivalence
No,
principle?
no. So say the Einstein principle and the strong equivalence principle. What exactly is the difference, as in?
Between these two?
Yeah.
So when we talk about the gravitational laws, we're sort of talking about the effect of gravity on gravity. Okay, and what do we mean by gravity on gravity? Well, gravitational binding energy you can think of as energy stored in a gravitational field. Okay, and now that gravitational field is freely falling in another gravitational field.
Okay, so it's like the cumulative effect of every gravitational force felt.
Yeah.
Okay, okay. Okay, thank you.
Okay. Okay, so the point is, so basically we'll take the version of the strong equivalence principle to be, there is, in a very simple way, there is no experiment that can distinguish between uniform acceleration and a uniform gravitational field. Okay, when we say no experiment, it means all laws of nature basically obey this equivalence principle. Okay, so now let's come to, without really going into the mathematics of it, okay, because general relativity will be basically built on this principle in the same way that special relativity is built on the principle of the speed of light being constant, okay, for all inertial observers. Okay, in the same way, general relativity will be built by adding this principle. Okay, and in fact, by adding this principle, okay, it will very strongly constrain the form of the laws, okay, and it's a new principle in addition to the ones that I had listed before, okay, but I mean, see, the thing is, Einstein realized on very physical grounds that this needed to be the right principle, this needs to be the right principle of nature. Now, it's not obvious why, okay, this should be the case, it just seems to be the case empirically, okay. So again, the genius of Einstein is figuring out what is the right physical principle, okay, and going from the right physical principle to the mathematics is complicated, right? But that is one part of how hard the problem is. But the really hard and creative part is coming up with what is the right physical principle, okay. Uh, so some implications of this equivalence principle. Okay, so let me just tell you two implications. Okay, and we'll see this mathematically in more detail how these manifest themselves. But let's just try to understand them physically. Okay, so the first thing is, one consequence of the equivalence principle is that light is going to be deflected in a gravitational field. That is, light will feel the effect of gravity and it will bend. Okay, this is something unexpected from Newtonian mechanics, because in Newtonian mechanics, light or photons you think of as having zero mass, and therefore they should not experience a gravitational field. Okay, so this would be sort of like the first point. Well, actually, Newton's laws are kind of ambiguous about it, because you have this, and then the question is, what happens at m is equal to 0, right? Do I take this going to 0 first? Do I take this going to 0, or do I just assume that both stay equivalent even the limit m goes to 0? Of course, there's no sense by what you mean by limit. It's just a question of what is the law for massless particles. Okay, but when you take the version of the statement to mean this equivalence principle to be the strong equivalence principle, we'll see that also means light should be deflected in a gravitational field. That is, light should also feel the effect of gravity. Okay, the second effect, which is also interesting, is that if you have clocks in a gravitational field, okay, the clocks which are in a gravitational field will run more slowly than clocks which are outside a gravitational field. Okay, or in other words, if you think, so we'll see what this is. Okay, so this effect is what is called gravitational time dilation. So if I have clocks which are in a gravitational field, okay, not freely falling, okay, just in a gravitational field, then they would run more slowly. Okay, so let's see how these two principles, or sorry, how the equivalence principle implies these two effects. Okay, so let's do the first one first. Okay, so here imagine that you are in a, now by the equivalence principle, here you are in a lift. Okay, and this is like scenario 3 above. Okay, now I'm being accelerated upwards. Okay, and now someone shines a beam of light, and this, let's say the walls of the box are transparent and the light goes through. Okay, And now we know what light does in inertial reference frames, right? It would just travel in a sort of in a straight line in an inertial reference frame. Okay, but we know that the box and the apples, everything is being accelerated upwards. Okay, and everything within the box would appear to feel pseudo forces, but that's because the elevator is moving upwards. Okay, you can think of that as your reference frame or your coordinate axes, which are moving upwards. Okay, so even if there's no physical elevator, it's like your coordinate system is being accelerated upwards. Okay, now you would experience pseudo forces because the y coordinates would appear to change, but to an inertial observer, the y coordinate is not really changing. Okay, it's at the same position. It's your coordinate system which is being accelerated. Now, the same thing would be true for light as well. Okay, because as I'm going up, my coordinate system moves up, and therefore the light appears to move down relative to the elevator. Okay, so in an accelerated reference frame, light also appears to experience these kind of pseudo forces. Okay, that is a sort of obvious, right? Because your frame is accelerating, light is not accelerating. Okay, now by the equivalence principle, this must be exactly what should happen in a uniform gravitational field. That is, in a uniform gravitational field, the person in the elevator should experience exactly the same thing. Apple should fall down, internal organs should fall down, light should fall down. Okay, so light should fall in a gravitational field, light should experience the effect of gravity. Okay, this is the first consequence of the equivalence principle. Okay, quite remarkable. All right, the second consequence is even more interesting. Okay, and we can think about it from the perspective of the so-called twin paradox. Okay, in special relativity, which is now imagine that you have two twins. Okay, twin 1 and twin 2. Twin 2 is put on a rocket ship and sent off to a faraway planet, and it travels at a speed very close to the speed of light. Okay, now this twin, okay, will obviously experience gravitational time dilation. Okay, and so time would appear to slow down for them. And if they make a round trip, that is, they come back to the original twin's location, okay, you would find that twin 2 has aged less. So twin 2 might have aged only 5 years, okay, and the original twin who's there might have aged 100 years. Okay, now this seems like a paradox because according to the laws of special relativity, the twin paradox is that basically there should be no way to distinguish between two different inertial observers, and therefore there's no way to tell for whom time is dilating, because according to twin 2, who is moving this way, okay, twin 1 has a speed in the opposite direction, and therefore twin 1 should be the one who is experiencing time dilation. Okay, that is, twin 1's clock should be slowing down. But this is a false equivalence because twin 2 is doing something very special. Twin 2 actually first travels at a uniform speed and then accelerates or decelerates and then accelerates in the opposite direction. Okay, so twin 2 is not an inertial observer, rather they're an accelerating observer. So if you draw the space-time diagrams, this is CT and X, this is twin 2, this is twin 1, who is just at rest at some position X, and we're in their reference frame. So only the time coordinate changes, their X coordinates stay the same. According to them, twin 1 basically follows this path. Okay, they travel some distance X, then they turn around and accelerate and come back this way. Okay, with a speed less than the speed of light, but still at a high enough speed that you experience significant relativistic time dilation. Now, twin 1 is, this is twin 2. Okay, twin 2 is in the spacecraft. Okay, now twin 2 basically experiences a proper time which is longer than that of twin 1. And proper time is something that everyone agrees on. Okay, so proper time is this. Okay, this is c squared d tau square. Okay, and you can see that, for example, if this observer, if this twin 2 is going almost at the speed of light, okay, then between this point and this point, because it's a light-like interval, okay, this time interval is very small or close to 0. Okay, it's 0 if exactly it's traveling at the speed of light, and so almost no time would elapse, just like no time elapses for a light beam, right? If you're traveling along with the light beam, so time slows down as they go here, and time slows down when it comes back. Okay, and if the acceleration is infinite, you can accelerate from a speed of c towards the right and turn it around and go with the speed c towards the left. Okay, there's no limit on the amount of acceleration you can have in special relativity, just on the velocities. So the velocity cannot exceed the speed of light, but that's the only constraint. Okay, and so this observer okay, twin 2 can basically experience almost no time elapsed. Okay, so you can travel between distant planets in principle if you could get up to such speeds without aging much. Okay, so for you, not much time would have passed. Okay, so this is the twin paradox. Okay, that is, if you're in an accelerate, if twin 2 sort of accelerates, okay, time would appear to slow down for them. Okay. And you can think about this turnaround as not being due to sort of an instantaneous acceleration at this turnaround point, but rather you can think about it as continuously decelerating, and then the acceleration is in this direction, and then they turn around. Okay, so if you're again in a uniform gravitational field, a uniform gravitational field is like having, let's say, a uniform acceleration. Okay, it's like being in an accelerated frame of reference, and therefore twin 2, who is in this accelerated frame of reference, okay, should experience gravitational time dilation. Okay, that is, time should appear to slow down for them in a gravitational field. Okay, so this is one way to understand clocks in a gravitational field. Okay, run more slowly than clocks outside a gravitational field. Again, this is a consequence of the equivalence principle. Being in a gravitational field, assuming you're not freely falling, is equivalent to being uniformly accelerated. If I think about a uniform gravitational field, and therefore, if I'm in an accelerated frame of reference, I know that I will experience time dilation, and my time will appear to slow down, and therefore clocks in a gravitational field run more slowly than clocks outside a gravitational field. Okay, truly remarkable. Okay. All right. Okay. So so let me summarize. Okay. So let me just summarize this part, which was still part of lecture 2. Okay. So we can attempt a naive merger of special relativity and gravity. Okay, that would require the simple principles that we wrote down earlier of trying to guess what is the form of the tensor structure of the gravitational field. Is it a scalar? Is it a tensor, a rank 2 tensor, or so on? And then we try to write down laws which are consistent with the principles of special relativity. That is, we try to write down some tensor is equal to some other tensor, or you try to, and plus you try to use some additional principles to try to constrain the form of the law. Okay. Now, what Einstein realized is that there is something very special about gravity. There is an additional principle that you need to assume. Okay, this principle is very special to gravity, which is the equivalence principle. And the equivalence principle implies that locally, gravity is indistinguishable from an accelerating frame of reference. Okay, so gravity is special in some way. And this strong equivalence principle, okay, will lead to non-linear laws for interaction of the gravitational field with particles. Okay, so that is Newton's laws. One of the principles that we had guessed could be a principle is linearity. It turns out that linearity will not be consistent with the equivalence principle. Okay, so you'll need to assume non-linear laws, and therefore the laws themselves will be more complicated. Okay, so we'll modify the basic principles. Okay, sorry. And this modification will lead to a change of the framework. Okay, so just like when you assumed additional principles, you found that you went from Galilean relativity to special relativity, then the laws of nature themselves have to conform to these new symmetries that arose as a consequence of special relativity. That is, we postulated that the speed of light c is the same for all observers. The consequence that this leads to is that there's a mathematical structure of symmetries described by the group, the Lorentz group, and this constrains the laws. Okay, so similarly, we'll see that there will be this principle that we assume, which is the equivalence principle. Mathematically, the consequence of this will be that there's a group of symmetries called diffeomorphisms, okay, which is a fancy way of saying that that under a coordinate transformation, any arbitrary non-linear coordinate transformation, okay, the laws of physics should take the same form. Okay, under arbitrary coordinate transformations. Okay, one arbitrary coordinate transformation is going to an accelerated frame of reference, but other arbitrary coordinate transformations exist, and all of them would give rise to pseudo forces. Okay, and basically the statement is that the laws of physics should be invariant under these arbitrary coordinate transformations. They should preserve the same form. Okay, and this will also give rise to additional constraints on the laws. Okay, so this is the rough idea, okay, of what we're going to do. Okay, we're going to take the principle, use it to build sort of a mathematical framework. And this mathematical framework is not a law, but it's rather a constraint on the laws. And then what we will actually do is we will actually derive laws which are consistent with these principles. Okay, for the gravitational field. It turns out that this rule will be quite restrictive. Okay, and therefore the laws are again, with some assumptions, almost uniquely determined. Okay, so the laws for gravity, the modification of Newton's laws, all of these will be very highly constrained. Any questions here? Okay. So now let me just come to something else. Since we've seen that acceleration or uniform acceleration is equivalent to uniform gravitational fields, it's useful to try to understand what you mean by uniform acceleration in special relativity. Okay, because everything that we did was in the context of Newtonian relativity, and we know that, you know, at least you expect special relativity to apply. So we want to we don't want to throw away special relativity. It seems to work really well. So we want to combine special relativity with the equivalence principle. Okay, and so what we need to do is we need to understand in special relativity, we need to understand acceleration, okay, or accelerated observers. Okay, and as we'll see, okay, acceleration in special relativity, although I told you that, you know, there's no constraint on the amount of acceleration that you can have, okay, the kind of accelerating reference frames that you can have, okay, and their physical interpretation is quite different in special relativity. So we'll try to understand some of these differences today. Okay, so let's come to the first thing in special relativity, okay, which is, let's suppose that you try to construct. So we'll assume now that special relativity is the right framework for the laws of nature. Okay, now let's assume that you try to give up in some reference frame S. Okay, you try to give a particle an acceleration a. So what does that mean? It means d square x by dt square in that reference frame, that inertial reference frame, is a. Okay, and this a we'll assume is a constant. Okay, so this kind of equation, okay, with a constant acceleration cannot be consistent with the framework of special relativity for all times. Okay, this can be true for some instant of time. It cannot be true at all times. Okay, in the reference frame S. Let's see why. Okay. So this cannot describe the world line of a particle in special relativity. That is, at all times, this cannot be the right equation that describes the motion of the particle. Okay, so why is that? Well, if you look at this equation, what it tells you is v is equal to dx by dt, and if I integrate this, then I get speed is equal to at, okay, plus a constant. But let's ignore that constant. So v is equal to at. So what does that mean? Well, that means that the speed increases linearly with time in reference frame S, which means that eventually the speed will exceed the speed of light. Okay, so if I continue to accelerate with the uniform acceleration, the speed will exceed the speed of light. This cannot happen, okay, for any physical particle. So therefore, uniform acceleration of this form is just not allowed in special relativity. Okay, it cannot happen. Okay, at the point where you're about to exceed the speed of light, you will need to pump in infinite amount of energy to actually get the particle up to the speed of light. So it's actually not going to be possible. Okay. So this is only what is allowed by kinematics. Okay, you actually have to see what is allowed by dynamics, like what are the forms of the forces. Okay, and do those forces allow you to accelerate? Okay, so for example, I mean, if you've taken the STR course last semester, you would have seen that if you apply an electric field, right, and if I'm accelerating an electric field, the speed will never exceed the speed of light. Okay, even in a uniform electric field. Okay. Now the other thing is, if you were to assume that this law were true, okay, which it is true in Newtonian mechanics or Galilean relativity, if you take x is equal to half at square, the trajectory of such a particle, if you draw the world line, is parabolic. Okay, so in the space of x versus t, okay, you get this parabolic shape. Okay, and a is roughly a measure of the curvature of this parabola. Okay, so if a is larger, okay, then the curvature is sharper. Okay, so I curve more sharply. Okay, for larger accelerations. Okay, you turn around faster. Okay, so now what we'd like to do is, okay, so this doesn't work in special relativity. So the question is, how do you describe particles with constant acceleration in special relativity? Okay, so if you want to describe constant acceleration, you can have constant acceleration in something called the MCRF. Okay, so what does MCRF stand for? MCRF stands for momentarily, okay, that is instantaneously, co-moving rest frame. Okay, so if you're in a frame S and the particle is, sorry, if you're in some frame S prime and you have a particle which is moving, okay, you locate the particle at some instant of time, and then you switch to a coordinate system which is moving with the same speed as this particle, so that momentarily in that reference frame, that new reference frame, okay, of let's call it the new reference frame, let's call it S. Okay, in that new reference frame, the particle is momentarily, that is at that instant of time, it is at rest. Okay, that is what we mean by a momentarily co-moving, that is, it's moving along with the particle rest frame. Okay, now if the particle is accelerating, at the next instant of time, its speed will change. Okay, which means that the frame S that you chose will no longer be co-moving with the particle. Okay, so it's only co-moving with the particle at that instant of time. At a later instant of time or an earlier instant of time, it may not be co-moving with the particle. That's why it's only at that instant of time that this is co-moving with the particle. Okay, and at that instant of time, the particle is at rest in that frame S. Okay, it's a momentarily co-moving rest frame. So in this momentarily co-moving rest frame, okay, you can ask in that frame S, okay, which is moving with the particle, let's pick it at some instant of time, okay, and at that instant of time, we want to know what is the force velocity of the particle in that frame, and what is the force acceleration of the particle in that frame, okay. So we switch to frame S, which is momentarily co-moving, and we have coordinates x0, x1, x2, x3, where x0 is ct, x1 is x, x2 is y, x3 is z. Okay, and the force velocity is u alpha, which is dx alpha dt. Okay, and this is the time. Sorry. Okay, so I'll just define it this way, and what we'll see is that the time in the MCRF actually describes the is related to the proper time. Okay, so in some sense, this really is the force velocity. Okay, but at that instant of time, dx alpha d tau is just 1, 0, 0, 0, which corresponds to u is equal to 0. Okay, so it has no speed. Okay, it's at rest in that reference frame. Okay, however, I can consider a particle which has an acceleration. Okay, in this reference frame S. So even though in this frame S, the particle is momentarily at rest, it can have an acceleration. Okay, and so we'll write down the acceleration for vector. So we'll write down an acceleration a alpha, which is d square x alpha dt square. Okay, at least we'll just write the three components of this, and we'll take one component of it, let's say in the x direction, to be a. Okay, so this is the acceleration in the frame S, which is the MCRF, and we will assume that this a is a constant. Okay, which means at the next instant of time, okay, this particle would have moved to a different position. It would be traveling with a different speed. Okay, its speed would be different both in the original frame S prime, and its speed would be different as compared to what it was in the frame S. In the frame S, at one instant, which was the MCRF, it was at rest. Okay, the MCRF is actually not one single frame, right? It's moving with the particle. So every instant that the particle moves, you have to change your reference frame to keep up with the particle. Okay, so so as I'm moving with this particle, okay, at one instant of time, this is my reference frame. At another instant of time, there's a different speed and therefore a different reference frame. Okay, and also I have to choose my origin of the coordinate system appropriately. Okay, I can choose it arbitrarily, but remember that the origin of this coordinate system and the origin of this coordinate system can also be different. Okay, so so this is MCRF1, this is MCRF2. Okay, and these are changing. And so as seen in the original MCRF, after the particle has moved, the particle is now at a different position and has a non-zero speed as measured in the original MCRF. But if I switch again to the new MCRF, in the new MCRF, the particle is at rest. Okay, that's what we mean by the MCRF, is I don't stay in this reference frame S S and S double prime, or S double prime and S triple prime, I don't stay in this reference frame once the particle moves. Okay, I switch over to a new inertial reference frame. Okay, why do we keep switching to inertial reference frames? Because we know that the Minkowski transformations are valid only between inertial reference frames. Okay, that's why we have to keep switching to different inertial reference frames. That's the only law that we're sure of. Okay, of what physics looks like for different inertial observers. All right, so so now if I look in the MCRF at some instant of time, okay, this is the space-time diagram. Okay, so the particle is at some location x and it has zero velocity. Okay, the particle is at rest, but it has an acceleration. Okay, it has an acceleration. Okay, so now let me just clear up the nomenclature. So at some time along the trajectory, I label the MCRF of the particle by a frame S. Okay, and S prime will be some fixed inertial reference frame. Okay, so let's say S prime is the frame that we started looking at this particle in, and the MCRF is this frame S. Okay, over here. This is just the label that I'll use. Okay, and in the coordinates of S prime, which is the original coordinate system, okay, there are coordinates x prime and t prime, and the particle is following some trajectory. Okay, I can either write the trajectory as some x prime of t prime, or I can write it parametrically as some x prime of some parameter alpha, and t prime as some parameter alpha. Okay, and as I vary alpha, I move to different space-time points, and that describes the trajectory of the particle. Okay, so this is called a parametric representation of the trajectory. Okay, so now in the original reference frame S prime, okay, with coordinates x prime and t prime, we'll take some instant of time t prime, okay, and in that reference frame S prime, okay, which is the fixed inertial reference frame, the particle is assumed to have some speed u prime or ux prime, which is nothing but dx prime by dt prime at some fixed t prime. Okay, that's the definition of speed. Now, assuming that that this particle has a constant acceleration in its MCRF. Okay, in its MCRF it has a constant acceleration, not in frame S prime. We saw that that's impossible for it to have constant acceleration in frame S prime, because then it would accelerate to a speed greater than the speed of light. But what we will see is that it is possible for the particle to have a constant acceleration in its momentarily co-moving rest frame. Okay, and what we would like to do is find the trajectory, okay, the parametric trajectory of this accelerated particle as seen in the frame S prime. Okay, so in the frame S prime, we would like to find out what is this parametric form of the trajectory. Okay, what we know is that in the in the MCRF, it has a constant acceleration. Okay, so that's the problem that we're going to solve now. Any questions at this point before I try to actually solve this problem? Yeah, Utkarsh.
So how exactly are we ensuring that the S prime does not have the constant acceleration of the particle?
We'll see that will happen. Okay, under this assumption that that the acceleration in the MCRF is constant, we'll see that in S prime the acceleration will not be constant.
Okay.
Okay, it'll come out for it. I mean, I've not proved that this will give you a consistent trajectory. What we'll see is that it does give you a consistent trajectory where you don't exceed the speed of light. Okay, Malvika?
So we are starting out with assuming that in MCRF acceleration is constant.
Yes, that's a starting assumption. Yes.
Okay, and it's justified by the results that we get later.
Yes. Yes, absolutely. Yeah. Okay, I've not shown you that this will give you a consistent trajectory because again, this is kinematics, it's not dynamics, right? So I don't know if this is a law which is consistent with the laws of special relativity, but what we'll see is it does give you something that's consistent with the laws of special relativity. You don't exceed the speed of light. Okay. Okay, so now if you're in the MCRF S, Okay. What we said is that dx alpha dt is 1 0 0 0. Okay, this is the 4 vector for velocity. Okay, strictly speaking, the 4 vector for velocity is d tau, dx alpha d tau. What we'll see is that d tau is the same as dt if you're in the MCRF. Okay, that's actually quite easy to see. Let's see, to direct this down. Yeah. Okay. So. Okay. Anyway, let me just proceed slowly. So dx by dt. Okay, that is if I take, let's say, the one component of this, dx by dt is 0. Okay, that is I have no velocity in the MCRF. That's an obvious statement, right? That's by definition what we mean by the MCRF. Okay, but what it means is after a small time interval dt in the MCRF, dx will be 0. Okay, that is the particle will not move. Okay, it will move at sort of second order in dt. Okay, because it has a constant acceleration, dx will be after a time dt will be half a dt square. Okay, so it'll sort of at second order in dt it will it'll have some displacement. At first order in dt it has no displacement. Okay, after a time dt. Okay, that should be familiar to you from just standard basic acceleration, right? So after the time interval dt, the particle will acquire a velocity. Okay, and this velocity will be linearly growing in dt. Okay, so if I take the acceleration, which is du alpha dt, okay, and I take the x component of the acceleration, dux dt is that constant acceleration a, as we had assumed earlier. Okay, so in a time dt, the particle will pick up a speed dux, which is a times dt. Okay, so in the small time interval dt, the particle picks up a displacement which is negligible. Okay, it's at order dt square, but it picks up a small velocity. Okay, that small velocity is a times dt. Okay, so basically the particle moves from some x to x plus dx in a time t to t plus dt. Dx is 0 at leading order in dt. Okay, it's non-zero at higher order in dt square. Okay, now if you ask, so the particle started at some x t and then it moved to some x plus dx t plus dt. This is in the MCRF. Okay, so this is so to be clear, what I mean is the MCRF is some frame S. After the particle moves, I will continue to stick with that same frame S, even though the MCRF is now a different MCRF because the particle has moved and has a new velocity. Okay, so we'll stick with this frame S, okay, and describe the new position of the particle. And we'll consider the space-time interval between these 2 points. Okay, so that space-time interval is c square d tau square. I'll just write this some proper time, times c square dt square minus dx square. And dx is 0, okay, because the particle has not moved at leading order in dt. And so this is just c square dt square. Okay, so at leading order, basically the proper time that has elapsed for the particle, which is like if the particle was actually carrying a physical clock with it, the amount of time that would have elapsed, the d tau interval, would be exactly the same as the dt interval that elapses in the MCRF. Okay, so the clock in the MCRF in a small time interval measures the proper time seen by the particle. Okay, since dx is 0. Okay, so d tau is basically just the same as dt. Okay, for small enough time intervals. Okay, so the time interval dt in the frame S just describes the proper time d tau of the particle, and this proper time is a Lorentz invariant quantity. Okay, so all observers will agree on the amount of time d tau that has elapsed between the particle moving from here to here. Okay, they will just calculate it in different ways. Okay, so for example, if you're in the frame S prime, which was the that original reference frame in which this particle is moving. Okay, the particle would have moved from some x prime t prime to some x prime plus dx prime and t prime plus dt prime. And what we would say is c square d tau square, that proper time interval that we calculate, we would calculate in the frame S prime by taking the 4 vector difference between these two and squaring it. Okay, in other words, we calculate c square dt prime square minus dx prime square. Okay, and these two should be the same. Okay, because this is a Lorentz invariant quantity. Okay. Okay, so now the other thing is, sorry, I think I did this. Yeah, so now in the MCRF, okay, we've also seen that the velocity changes. Okay, so as I move from the point, x prime t prime to the point x prime plus dx prime and t prime plus dt prime, the speed of the particle should change. Okay, the speed was ux prime in frame s prime, so the speed should now become some ux prime plus dux prime. Okay, in frame s, which is the MCRF, the speed ux is 0, that is instantaneously it's at rest, and then a time dt later, okay, the particle has picked up a speed ux plus dux. Again, ux is 0, so it just picks up the speed dux, and dux is just a times d tau, okay, as we discussed earlier. Okay, so now what we can do is we can relate the speed in the frame s prime to the speed in the frame s, because we know how fast the frame s is moving with respect to the frame s prime. S is the frame in which the particle is momentarily at rest. Okay, therefore S is the frame in which the particle in S has a speed relative to the frame S prime, which is just ux prime. Okay, that is, it's the speed at which the particle itself is moving at this instant of time. Okay, at this space-time point. So now we can just do a velocity transformation. Okay, and we can use this velocity transformation to figure out the speed in frame S prime at this instant of time relative to the speed in frame S, which is the MCRF at this instant of time. Okay, that is after the particle has moved and picked up this small extra speed. Okay, so the velocity transformation law is, this is the velocity in frame S prime. Okay, here. And we want the velocity in frame S, which is here. And to transform from S to S prime, we use the relative speed, which is ux prime, which is here. Okay, so it's like v plus u over 1 plus uv over c squared. Okay, so that's the rule that I'm using. So I'm putting 1 plus, again, this ux prime here, and this ux plus dux over here by c squared. Okay, so what is the result of this? The result of this is I'm going to be able to figure out what is the change in speed, that is, what is the change in speed ux prime, dux prime, as seen in the static inertial reference frame S prime. Okay, I don't want to know what happens in these MCRFs. I want to know what is happening in this inertial reference frame S prime. Okay, so if I simplify this, okay, so I won't walk through the math, though it's in the notes. Okay, so what you find is that dux prime, okay, is just equal to, all I did was plug in for dux. Okay, this is the extra speed which you pick up in the MCRF is a times d tau. So when I plug this in, okay, what you will eventually get is dux prime, that is the extra speed that you pick up in the inertial frame S prime, is equal to a times d tau, which is the acceleration that you pick up, which is the extra velocity that you pick up in the frame S, but times this extra factor. Okay, and this extra factor is velocity dependent. Okay, it's 1 minus ux prime square over c square. Okay, so and that's not surprising, right? Because the velocity transformation rule to go from this frame to this frame depends on ux prime. Okay, sorry, I know this might be a little fast because I'm going through math and I'm not deriving this, but I hope the physics of what I'm trying to do is clear. Okay, if not, please ask. Or let me know if it's too fast. Okay. So basically, this is the extra speed that you pick up in frame S prime. Okay, it's a times 1 minus ux prime over c square times d tau. Okay, so now what I can do is I can take this factor to the other side. I can divide both sides by 1 minus ux prime over c square, and I can get a differential equation. Okay, so this differential equation, I can now integrate this and find out the speed of the particle in frame S prime as a function of the proper time of the particle. Okay, so that is, after a amount of time tau for the particle has elapsed, I can figure out what is the speed as seen in the inertial frame S prime, okay, which is not an MCRF. Okay, so So I can integrate this equation, and the easiest way to do this is to convert ux prime to rapidity. So you write ux prime over c as tan h of eta prime, where eta prime is just the rapidity in frame S prime. Okay. So after you make this substitution, you find something very simple. Okay. You find that the rapidity in frame S prime, okay, is just equal to a times tau. Okay. So basically, instead of the speed growing linearly with time, with proper time, okay, it's the rapidity in the frame S prime that grows linearly with proper time. Okay, and there's no problem with rapidity. Rapidity can grow as fast as you want. Okay, and when eta goes to infinity, ux prime will approach c. Okay, so you will never exceed the speed of light. Okay, so you'll never exceed the speed of light as seen in frame S prime. So in other words, so if I write ux prime is dx prime by dt prime, okay, then this quantity is just tan hyperbolic, c times tan hyperbolic of this rapidity, which is a times tau. Okay, so the speed is basically some tan hyperbolic function. Okay, so if you start with initial condition that your speed is minus c, then a positive acceleration in the x direction will ensure that the speed eventually approaches plus c. Okay, so so unlike what you would expect if you just had constant acceleration in the frame S prime, where your speed just increases linearly with time. Okay, this is what would happen if dux prime dt prime was equal to a. Okay, your speed would increase linearly as a function of time. Okay, but now what you find is as a function of proper time. Okay, that is the time along the particle as measured by a clock moving with the particle. Your speed only changes between minus c and plus c. That is, it's bounded. Okay, so this is the question asked earlier, like, you know, how do we know that this rule is consistent? The constant acceleration in the MCRF is consistent with special relativity. Well, you can see manifestly now that it is consistent. Okay, your speed will never exceed the speed of light. Okay, as seen in we did this for one reference frame, but this would be true in any inertial reference frame because there's nothing special about the frame S prime. Okay, so in the frame S prime, in any inertial reference frame S prime, which is static, okay, in that inertial reference frame S prime, the speed will switch from minus c to plus c. Okay, so it really is like what you would expect for constant acceleration in one direction. Okay, so the acceleration basically turns you around. So you're going in the minus x direction, then you turn around and you come back in the positive x direction. Okay, so this is exactly what you would expect. Now, the only thing is here we found an expression for the velocity. What we'd like to do is find an expression for the actual trajectory of the particle. Okay, that is, we'd like to find what are x prime and t prime parametrically, maybe as functions of tau. Okay, because it seems like tau seems to be a good parameter to use to get the trajectory. Okay. All right. So now, as seen in the momentarily co-moving rest frame, okay, I told you the dx is 0 at leading order, and at higher order it's half a d tau square. Okay, so you actually have a little bit of motion. Okay, so now I can take d square x d tau square, and that is a. Okay, that's what we mean by constant acceleration in the MCRF. Okay, and again, remember d tau is just the amount of time that's elapsed in the MCRF, which is also the same as the proper time of the particle. Okay. So now what we can do is we can take just this leading order part of this expression, and what we can do is we can transform this into frame S prime. Okay, so we can get what is basically the interval dx prime. So here, here what we are doing is we're trying to get a rule for what is the change in velocity of the particle. Now, instead of trying to get a change in velocity, what we can try to do is get what is the change in coordinate. That is, oh, sorry. Sorry, okay. So what we're trying to do is instead of working out what is dux prime, now we're going to try to work out what is dx prime and what is dt prime. That is, what is the change in the coordinate itself. Okay, as seen in the reference frame S prime, compared with the fact that we know how much the coordinate has changed in the MCRF. Okay, in the MCRF we know dx is 0, and the time that has elapsed is just d tau. Okay, so if we know how much time and how much spatial interval there is between these 2 points, we can figure out how much time and spatial interval there is between these 2 points. Okay, it's just a standard Lorentz transformation. So let's just work out that Lorentz transformation. Okay, so the interval dx prime would be gamma. Okay, where this gamma depends on the relative speed between the frame s prime and s, which is just a function of ux prime, and it depends on dx, okay, and d tau. Okay, so I'm just transforming from dx d tau to dx prime dt prime. Okay, and remember that this is just dt. Okay, and I'm just doing a standard Lorentz transformation between the two. Okay, and what am I transforming by? I'm transforming by a velocity which is ux prime. Okay, so this is the transformation rule that I apply. Okay, and it's convenient to express the transformation of ux prime in terms of this parameter eta. Okay, which depends on tau. Okay, because as we've seen, ux prime by c is tan hyperbolic of eta. Okay, where eta is a tau by c. Okay, so it's convenient to work with this because gamma is cos hyperbolic. Okay, dx is 0, ux by c square is tan hyperbolic eta, and c d tau is c d tau as before. So when you work out all these factors, okay, tan hyperbolic is sine hyperbolic by cos hyperbolic. So this gives you sine hyperbolic eta times c d tau. And so I can write eta now in terms of a tau over c. Okay, so there should be an over c here. So I get dx prime, that is the amount of spatial distance between those 2 points as seen in the frame s prime, is sinh hyperbolic a tau by c times c d tau. Okay, and I can integrate this equation to get x prime as a function of tau. And what I would get is x prime is equal to c square by a times cos a tau over c square. Okay, so this only gives me the x prime. I also need to do the same thing for dt prime. Okay, figure out what dt prime is, integrate that equation, and get t prime as a function of tau. Okay, so you can do this, and I'll leave it as a homework exercise to do this. Okay, but at the end of this, what you'll get is this is the parametric trajectory for the particle. Okay, what you get is ct prime is c square by a times sine hyperbolic a tau over c square, and x prime is c square by a times cos hyperbolic a tau over c square. Okay, so this is the parametric trajectory of the particle that we wanted to find. Okay, and what is special about this trajectory? This trajectory is such that it has constant acceleration a in the MCRF. Okay, and as we've seen, this is consistent with the laws of special relativity because the speed starts at minus c, goes up to plus c. Okay, and never crosses c. Okay. Yeah, let me take a few questions. Utkarsh?
I don't think that there will be c square in the denominator of cos h and sin h.
It's c, sorry, not c square.
Yeah.
Thanks. Sarnik?
Yeah, so this approach would also work if the acceleration was variable in the MRCF, right?
Yeah, it's just that the integration you do would be different because a would be a function of tau then.
Okay.
Right, and so if a is a function of tau, then you have to integrate it, and it depends on how a changes as a function of tau.
Mm-hmm. Okay, sir.
Utkarsh?
Yeah, one more thing. What will the proper time of this particle mean? Because we don't have any interval, have any frame where it is like at rest. So what will the tau mean? The integrated tau.
Okay. So it's basically, you can think of it as, so it's one way to think about it is so it is the integration of the small dt prime time intervals in where those dt prime time, those dt time intervals where I am momentarily in a frame which is at rest with the particle. I measure amount of time dt. Then I move along with the particle to another frame, measure the amount of time dt in that frame. Okay, then I move along with the particle, measure an extra amount of time dt. So in some sense, this is really measuring the amount of time in the rest frame of the accelerating particle. Okay, by rest frame, I mean a series of snapshots of momentarily co-moving rest frames.
Okay.
Okay, so that is the sense in which you can think of this as the time on a clock moving with this particle.
Sir, do you mean that co-moving frame and the rest frame are the same?
Instantaneously, they're the same, but the co-moving frame keeps changing as the particle moves, right? And sorry, yes, momentarily co-moving rest frame means it's a rest frame, right? Except it keeps changing as the particle moves.
Okay.
So in every time you measure a dt, that's fine, but the next dt that you measure will have to be in a new reference frame, which is in the new frame in which the particle is at rest.
Okay.
Okay. And the other special property of tau is that it's Lorentz invariant, which means all observers have a way of calculating d tau which everyone agrees on, right? But they might calculate it in a different way in their coordinate system, right? As we've seen in frame S prime, they calculate it as dt prime square minus dx prime square.
Sir, just a small thing. Can you scroll up a little bit?
Yeah.
Right. So yeah, you've substituted neta prime as a tau by c. Is there a reason we've introduced another c normalization?
Where? Here, this C?
Ux prime by c is equal to tan hyperbolic neta, right? Neta prime, eta prime.
Sorry, one second. This one?
Part,
This one?
yeah.
Yeah. So ux prime by c is tan. So on dimensional grounds, of course, it's easy to see that, right? I think I might have gone wrong here.
Oh, okay.
I think it was really by c over here.
Right. Okay.
Okay.
Yeah.
This quantity is dimensional. Rapidity is dimensionless. So that's. I may not. I may have been sloppy with factors of c. Okay, you can restore them on dimensional grounds wherever needed. Okay, but the final expression is correct. This one. Okay, this is the one you can trust. Okay, and in fact, going ahead in the GR course, we're going to drop C. Okay, and you can restore it on dimensional grounds, but we won't be doing that. Okay, so so now if you look at this, okay, so let's do an expansion for small tau. Okay, for small tau, this is basically equal to c times tau plus order tau cube. Okay, this is an expansion of sine hyperbolic. Sine hyperbolic has a similar expansion to sine. Okay, for small tau, and similarly cos hyperbolic for small enough tau has a similar expansion to cos. Okay, so it's just half a tau square. So what you see is parametrically, okay, for small times, t prime is basically just the same thing as tau. And the motion of the particle x prime is equal to half a tau square, which is x prime is half a t prime square. So for small enough time intervals, the motion is just like your parabolic motion. Okay, it's just what you would expect. Okay, and let's just do a quick consistency check on this expression. So if you take dx prime by dt prime, okay, dx prime by dt prime, dx prime will give you sine hyperbolic, dt prime will give you cos hyperbolic, the ratio will give you tan hyperbolic. And as we've seen, tan hyperbolic a tau by c is exactly what we call the velocity in frame s prime. Okay. The other thing about this trajectory is you can eliminate this parameter tau. Okay, because this is a parametric trajectory, but you can eliminate the parameter tau to get the form of the trajectory. And to eliminate it, you simply take the square of this and the square of this and subtract them. Okay, so cos square minus sin square is 1. So you'll get x square minus ct prime square. Okay, this is equal to c square over a whole square. Okay, and this is the equation for a hyperbola. Okay, so if I plot the trajectory in the frame s prime, so now we can finally plot the trajectory. Okay, and this is nice because it will give us a visualization of what the trajectory will look like in frame s prime. So in the frame s prime, okay, where you have coordinates x prime and t prime, and what are the asymptotes of this hyperbola? They're the lines x. So this is of the form xy is equal to constant. Okay, or instead of xy, I'm writing it as x minus y into x plus y is constant. Okay, so the asymptotes are the lines x minus y equal to 0 and x plus y equal to 0. Or in other words, x prime is equal to ct prime and x prime is equal to minus ct prime. Okay, these are the asymptotes of the hyperbola. And we're only considering the positive part of the hyperbola. That is, we're considering only, I mean, we started with only x prime greater than 0. So we're not going to draw the negative branch of the hyperbola. And the trajectory looks like this. Okay, it's a hyperbola with those asymptotes. And where does it intersect the x-axis? Well, it intersects the x-axis at the point where t prime is equal to 0. T prime is 0 at tau is equal to 0. At tau is equal to 0, x prime is just c squared by a. Cosh hyperbolic is 1. Okay, so it intersects the x-axis at the point c squared by a. Okay, and then it asymptotes to these null directions. Okay, these are the directions along which light would move. Okay, and what you can see is that here at this point, okay, this is the point which is t prime is 0, but is also the point where tau is 0. Okay, because as we've seen, when tau is 0, t prime is 0. Okay, when t prime is 0, tau is 0, and you're over here, and the velocity is 0. Okay, that is, you're only moving in the time direction. As time passes, okay, you're picking up more and more speed so that you start tilting this way. Okay, but you tilt in such a way that you will never exceed a 45-degree direction. Okay, so that your speed never exceeds the speed of light. Okay, as we've seen earlier, the speed only goes between minus c and plus c. Okay, this is ux prime as a function of tau. Okay, and tau is a parameter that describes how much time has elapsed on this trajectory. Okay, it's not the same as t prime. Okay, t prime is the time that has elapsed in this inertial frame s prime. Okay, so tau is some parametric way of parameterizing the proper time along this trajectory. Okay. Now you could also ask a couple of different questions. Okay, you can ask what is the so here are a couple of questions that you could ask. Okay, so the first question that you could ask is what is the acceleration as seen in the frame s prime? Okay, because we said that, okay, this corresponds to a particle which has constant acceleration in its MCRF. But what acceleration does it have in this inertial frame s prime? Okay, so in the inertial frame s prime, okay, what I can do is I can calculate its its 4 vector acceleration. Okay, that is, I can calculate a prime mu, which is defined as d square x prime mu by d tau square. Okay, and this you can work it out again. Okay, you just have to differentiate t prime with respect to tau and x prime with respect to tau twice. Okay, both of these have to be differentiated twice, and sine hyperbolic you differentiate twice, you get sine hyperbolic. Cos hyperbolic you differentiate twice, you get cos hyperbolic. So what you get is something like sine hyperbolic a tau over c square, cos a tau over c square. Okay, so this is the 4 vector acceleration or the 4 acceleration in the frame s prime, and you can clearly see that the 4 acceleration in the frame s prime is not a constant. Okay, so the 4 acceleration in the frame s prime is changing. Okay, and if you like, you can write this in terms of the 0th component is proportional to the time coordinate of the particle. The first, the x component is proportional to the x coordinate of the particle. Okay. So this is what the 4 acceleration looks like. But you could ask something more physical. Okay, this tau is again proper time, but you could ask something more physical, which is if I really calculate the acceleration, which is d square x prime by dt prime square. That's after all what we would think of as the acceleration in frame s prime. This is not the 4 acceleration, but it's really the acceleration d square x prime by dt prime square. Okay, in the frame s. So the way to calculate this is you calculate dx prime dt prime and then differentiate with respect to t prime. Now dx prime dt prime we know with respect to tau, right? Because this is just tan. This velocity we know is tan hyperbolic of a tau by c. So it's easier to differentiate with respect to tau. Okay, so we differentiate with respect to tau and use the chain rule to write this as dt prime over d tau. Okay, so divided by dt prime over d tau. So what you would get is so when you differentiate this with respect to tau, what you get is something proportional to a times secant hyperbolic square a tau over c square. That comes from this differentiation. Tan hyperbolic differentiation is secant h square. And dt prime d tau is cosh of a tau over c. Okay, so when you put it together, the acceleration seen in frame s prime is a over cosh cube a tau over c. Okay, so what does this look like? Well, if you make a plot of this as a function of tau again, as a function of tau, this is what the acceleration looks like. Okay, so the acceleration at large tau, cosh cube goes to infinity. goes to infinity as tau goes to plus minus infinity. Cosh is symmetric in its argument. Okay, so at large tau, the acceleration goes to 0 in the frame S prime. At small at tau goes to 0. Okay, the cosh is 1 and the acceleration becomes a. Okay, so in the MCRF the acceleration was a, but in the frame S prime the acceleration starts off as 0, increases till it becomes a, and then decreases. Okay, that's easy to see from the trajectory also. Okay, see, initially the velocity is minus c and it doesn't change much. Okay, it's changing very slowly, so the acceleration is very small. Then at some point the acceleration actually becomes very large. Okay, this is where you're trying to curve around. Okay, and you're changing direction. This is where the acceleration is maximum and the acceleration is a. Okay, and finally again, once you pick up enough speed in the frame S prime, your speed cannot change more. It cannot increase much larger. I mean, to c, you get close to c, but then your speed cannot change much. So again, your acceleration goes to 0. Okay, so the acceleration first starts off as 0, then increases to a, and then decreases. Okay, so instead of maintaining a constant acceleration a, which we already saw is not allowed, right, in the frame S prime, your acceleration first increases and then decreases. Okay, and this is physically consistent, and it corresponds to the case of constant acceleration in the MCRF. Okay, so this point tau is equal to 0 is the point of maximum acceleration as seen in the frame S prime. Okay, now let me tell you some okay, so sorry, maybe I'll stop here. Okay, sorry, let me just finish one last thing and then we'll stop. Okay, I'll do this next part in the next class. Okay, so if I draw the trajectory of this particle, okay, so this is the particle with the hyperbolic asymptotes. Okay, and if I draw the parabola would have looked like this. Okay, and you can see that the slope of this parabola goes on decreasing, which means the speed goes on increasing. Okay, the speed is dx prime by dt prime. Okay, so the speed goes on increasing. So if the trajectory were parabolic, okay, the speed would go on increasing. Since it's hyperbolic, okay, this it basically slows down. Okay, as I mean, it stops accelerating. Okay, as it approaches the speed of plus c, and here as the speed is minus c. Okay, and near this point, which is tau is equal to 0, okay, the parabolic trajectory and the hyperbolic trajectory are almost the same. Okay, because as we see in the small tau expansion, okay, the hyperbolic trajectory is really around this region. It looks parabolic. Okay, it's once you start getting away from once the speed becomes large, then you can no longer have this parabolic trajectory. Okay, you switch over to this hyperbolic trajectory, which is the only thing consistent with special relativity. Now, one peculiar feature of this entire thing is that if I look at this region of space, okay, which is beyond this light ray, okay, any point here, and I imagine trying to communicate with this particle by let's say shooting light beams or sending any kind of particle towards it. Even light beams will only travel along 45-degree lines on this diagram. Okay, so a light beam will never reach this particle. Okay, a light beam sent from anywhere, even very close to here, okay, but on the other side of this line, will never reach this particle. Okay, so this is a peculiar feature of special relativity. It's not something that happens in because of the finite speed of light. Okay, no signal can actually be sent from this entire magenta region of space-time. No signal can ever be sent to this observer from beyond this region. Okay, so this space-time region from which no signal will ever reach the particle, okay, or this boundary of that region is called a horizon. Okay, and this is very similar to the black hole event horizon that I mentioned in the very first class. Okay, a region from which light cannot escape and ever reach an outside observer. Okay, there we thought of black holes as, it's the force of gravity. Okay, here we're thinking about accelerating observers, but as we've seen, there's an equivalence between acceleration and gravity. Okay, and so this horizon is very similar to the horizon of a black hole. Okay, and we'll see this in more detail later in the class. Okay, so I'm going to stop here, and in the next class what we'll do is, instead of talking about one accelerated particle, what we'll do is we'll talk about a family of accelerated observers. Okay, and that's what we're going to build on in the next class. Okay, I'll pause for questions, and we can stop here. Yeah, Adyan?
So can you scroll up a little bit? A little more. So yeah, just down here where you define acceleration as dx by dt prime. The formula that you're using for dx prime by dt prime is the one we got by using the transformation laws for velocity, right?
This one?
C tan h a tau by c.
Oh, this one.
Yeah.
No, so what I did is, okay, so dx prime by dt prime, yes. Yes, exactly. So this was c tan h a tau by c,
Yeah,
that's right.
But this is the 4 velocity then. The 4 velocity is dx prime by d tau prime, right? It's not dx prime by dt prime.
No, this was the dx prime by dt prime. The 4 velocity was different. The 4 velocity, we didn't actually work out the 4 velocity. We only worked out the 3 velocity. So the 4 velocity in the MCRF is this, right? If you want to transform it, you would apply this transformation. Something like that, right? And that would give you cos theta sin theta 0, 0. Okay, which is the thing up, which is not this, but that's why I said I didn't derive it, but it's cos theta sin theta. That's the 4 velocity in the frame S prime.
Okay, thank you.
Yeah, tan hyperbolic is the 3 velocity. I mean, that's the thing that cannot exceed c, right?
Okay, yeah, I got it. Thank you.
Okay, any other questions? All right, let's stop here and then we'll meet on Thursday. Okay, see you. Bye-bye.
Thank you. Thank you.
Thank you, sir.
Thank you.